Welcome to section 1.2. In this section, we're just reminding ourselves of some basics, but I think there's some new definitions that may be present here. Some will be familiar, like intercepts, but others may be unfamiliar, like symmetry, and they ask about those right away. And so this is just in general. It's not really focused on lines. That's section 1.3. There will be lines in here, but there are varying graphs that you'll see because we're just concerned with concepts like intercepts and symmetry. And so I think you know about intercepts already. Apologize, I didn't check out what type of pen I was going to have here, so let me get rid of that and then also change this over. But so intercepts is, like, you remember, where it crosses, where a graph crosses either the x-axis or the y-axis. Okay, so we'll get these definitions out earlier. Well, if it's going to cross the x-axis, then let's just draw a picture. If it's going to cross the x-axis, it's going to be somewhere like that. So the unique part about this thing is not its x-coordinate, but its y-coordinate. No matter where I put this dot on the x-axis, the y-coordinate's always the same. So for here it's a comma 0. For here it's some kind of b comma 0. And for here it's some kind of c comma 0. But everything that's common is the 0. So if you want to find the x-axis, you want to find out um, what x is when y is 0. So here's where you let y be equal to 0, and you find x. Right? That's how we find that x-axis. To find the y-axis, very similarly, if I were to draw a picture, all of the x-coordinates are 0. And so here you let x be 0, and you find y. And you probably already knew that, right? So all x-intercepts are the form x comma 0, and all of the y-intercepts are of the form 0 comma specific y. And so they're going to ask us to find that. The other thing that they ask about is symmetry. And there's three types of symmetry that they're looking for. And I got to be careful as you hear that. You don't fall into one of three categories. There's a fourth category of having no symmetry with respect to anything. And so we talk about symmetry with respect. So I'll write that out. With respect to the x-axis. Okay, that's the first one that we'll look at. Let me do this through pictures. If you have a graph that's symmetric with respect to the x-axis, it looks like this. If we were to put a mirror on the x-axis, right, so this is the x-axis, then the graph would be completely mirrored below. So you've been through an Algebra 2 class, and so even though we're going to talk about it again in Chapter 2, this is not a function, right? This is a sideways opening parabola, a y-squared type of equation from your experience in the past, right? And that's what we're going to do. Rely upon your experience in the past and just make you better and better at the things that we've done in the past. Notice that if we're symmetric with respect to the x-axis, this distance right here, which I'll call a, is the same as this distance down here, right, which I'll call also a. Those are the same. Those a distances are exactly the same. So if you go out a certain x distance, right, so what makes a difference here and why these are connected like that is because the x was the same. So essentially this is how they're going to define x-axis symmetry, and it makes sense based upon the picture, that if xy is on the graph, then that implies x negative y is on the graph, right? Because that's what this point would be up here. Let me label them out in their respective colors. This point right here is xy. Or, even better stated by the way I have this, let me get an eraser in here. This is x a. And what's this right here? Well, it's the same x coordinate, but it's down negative a. It's down from the y-axis, right? It's a distance of a down from the x-axis, but in the negative direction. So that's what symmetry with respect to the x-axis is like. So how would I remember that? Very similar to how I remember where a graph, I'm sorry, where the x-intercept is. I let y be 0. So if I want to know about x-axis symmetry, I'm wondering for the same x, can I get two different y's? Can I get a y that's completely opposite? So if I know x, y is on the graph, if I plug in that exact same x, can I get a negative y? Or even better, if I plug in negative y, will it make a difference? And so we'll keep that in mind. So if I look for the thing that changed there, what it's saying is if you let if you change your y to a negative y, the x still stays the same. That might be a cleaner way to tell from a graph whether something is symmetric with respect to x-axis. Apologize, not from a graph, but from an equation. From a graph, you'll see it. 2, with respect to the y-axis. This is one that we're very familiar with as well. So the most common symmetric thing with respect to the y-axis is our normal parabola. And I didn't draw that very well. Let me see if I can draw that a little bit better. And here, same thing, except opposite way. Now my a's are going out from the x direction. So this one says if xy is on the graph, then so is negative xy, right? You change that. So very similar process. So if I want to know if something is symmetric with respect to the y-axis, I interchange the x with the negative x and see if I get the same y out. See if I get the same y height out. And then there's a third one, and that is symmetric with respect to the origin. And what this one's like is if xy is on the graph, then if you replaced x with negative x, you would get negative y. Or vice versa. If you place y with negative y, you get negative x. And so it's possible for something to have all three. I think we'll see that all three types of symmetry at the same time. But if we go with symmetric with respect to the origin, that would be something like the x cubed graph that we should be familiar with, which looks something like that, right? Um, Actually, that's not the x cubed. I'm too close to trig right here. Um, so actually, that was right. If I took a negative 1 and cubed it, I would get negative 1. So that was right. Apologize. And so we're going up like that as a snake-looking function. Well, this right here, remember this would be, if this was the x cubed function, this would be something like 2, 8, where negative 2, negative 8 is also on the graph. Notice that they're both the same values, but opposite signs from one another, and in both categories. So that's what symmetry with respect to the origin's like. So let's take a look at what our homework is going to look like. With this as a background, what we're going to have is something pretty nice. They're going to give us like one of the first questions that we'll have. So I'll put example 1. One of the first questions that I saw in the homework was plot the point negative 4, 1. So we're going to go do that. We're going to go plot negative 4, 1. So if I go plot negative 4, 1, I go 4 out, 1 up, and put a dot, right? And that's, pretty much basic pre-algebra. Perfect. Now they want us um, to put in, so let me put that as A, and then B, plot a point that is symmetric with respect to, I'm going to do WRT for with respect to the x-axis. Something like that. So if we had to do it with respect to the x-axis, where would that point be? So they're trying to make sure that we have a visual in there. So I'm going to come here and I'm going to do B in blue. So where would that point be? Well, if it's symmetric with respect to the x-axis, that's this horizontal line here. So where would it be? It'd be the same x distance out, but a different y value, not just any arbitrary one, the one that's the same distance down. So it's going to be right here, and all they want you to do is plot it, so you'll put a dot right there. But if I were to put it out, it's -4 and -1. So notice that my y value switched from positive to negative, but my x value stayed exactly the same. That's what this is trying to say. You keep the same x value, but your y value switches signs. So you know what C is going to say. C is going to say plot a point symmetric with respect to y. So if I go in here and in green put in that point, well, if it's going to be symmetric with respect to the y-axis, it's going to stay at the same y level, right? Your y is going to stay the same, but it's going to be flipped over that y-axis a perfect distance away, or basically being at 4, 1. And then I think you know what the last one's going to be, the last part of this problem. Part D is going to say symmetric with respect to the origin. Right? Same directions, right? A point symmetric with respect to the origin. Well, what happens there? We'll do that one in red. Let me come in here and highlight that in red so we can tie them all together. Well, two things have to change. I have to be basically in the other quadrant, right? The opposite quadrant. So I got to go, and I was at -4, 1. I got to be at 4, -1. Right down here. Or sorry, yeah, apologize. Let me take that negative off of there. 4, -1. That is changing both signs. So if we go up here and look at what happened, for the blue, which is the first one we did, we took our y and made it negative, but kept the same original x. From the original point for letter B, we took our x and made it the opposite sign, or in this case positive. And then for C, we took both x and y from the original point and made them the opposite sign and got the 4, -1. So it should go relatively quick. I know I'm just taking a little bit of time to explain this. So here's the second question that I want to go over with you that I saw. They gave me a function. Actually, it's not a function. They gave me a relationship. Y squared is equal to x squared plus 25. And here's what they want to know. They want to know, is 0, 5 on the graph? Is 5, 0 on the graph? And is -5, 0 on the graph? So, and they said mark all that apply, right? So, or in this case, I'm phrasing it like questions. It was little bullet points that you would just say, yeah, that's true. So, let's just try this. Hopefully, this is not daunting at all. They're saying if you plug in 0 for x, do you get 5 out for y? And I think the answer is yeah, right? If we plug 0 in for x squared, we would have, so if I work this one out, we'd have 0 for x and 5 for y. We'd have 5 squared. Does that really equal 0 squared plus 25? And the answer is yes. 25 is equal to 25. How about 5, 0? That would be, if I go look at 5, 0, it's a little bit different. 0 goes in for y. 5 goes in for x. And that's a no. That is not on the graph. Because 50 is not equal to 0. And then how about -5, 0? If we plugged in -5 for x, well, we're still going to get a 25 plus 25 out, and that's not going to be equal to 0. And so this one's a no as well. And so that's what you're looking at, just quickly plugging in points and seeing what works, what doesn't work. And just reminding you that these solutions that we're getting out are actually points along the graph. There's some things that we feel happen in Algebra 2 that students don't fully grasp, and that's why we bring them back up in pre-calc is so that we can get an idea of um, of of solidifying, some of these things that we did algebraically and things that we did graphically and merge them together. The next type of problem that I saw in there was giving us a graph like this. And so I'm going to try to draw it my best way that I can, right? And so this is -4, this is 4, and then we have these sideways opening parabolas that are centered here, right? So it's basically the graph of a hyperbola. And regardless of how poorly I draw it, these guys are completely mirrored from side to side, centered at -4, 1. And so they'll have a perfect picture of it. And so the question that they want to know is, what are the intercepts? And so no problem. The intercepts are -4, 0 and 4, 0. And they take them like that, and as you're going to type them into MyMathLab, they'll want a comma in between, and you'll hit return and be like, okay, good job. And then they want to know, is it symmetric with respect? So I'll put symmetry with respect to, and then they'll ask about each one. How about x-axis symmetry? Do we have x-axis symmetry? And the answer to that is yes. And so let me make this look a little bit better. The answer to that is yes. Do you see that happening? So as we look at this part of the graph right here is completely mirrored down here, right? Those are the same distance away. And again, it will be a little bit more clear. Same thing over here on the left-hand side. It would have to be everywhere. It couldn't just be in a portion of the graph. And so the answer is yes, absolutely. It's symmetric with respect to the x-axis. How about with respect to the y-axis? Well, let's look. Let's look at a portion of the graph that's to the left of the y-axis. Well, this is to the left of the y-axis. And look, it's completely mirrored over here. The distance that this curve is away from the y-axis at any given point is the same. So the difference that this curve is, the left-hand curve, away from the right-hand curve, well, the distance the left-hand curve is away from the y-axis and the right-hand curve is away from the y-axis is always the same, no matter which y value you pick. And so the answer here is also yes. Let me see if I can do some erasing here. Oops, too much erasing, but I can fix that. Okay. And then the final one is the origin. So from a graphical standpoint, to test for the origin, we'd want to look at this portion of the graph and see if it's mapped down here. And the answer is yes. So -4, 0 goes to +4, 0. And -5, maybe -1 goes to +5, -1. So everything is switched. So this is also symmetric about the origin. That's why I said I think we'd see one along the way that's symmetric about all three. Another problem that I saw in there is this one. Y squared is equal to x plus 81. They would like to know the intercepts. Okay, so let's find the intercepts. Well, in order to find the intercepts, let's find the y-intercepts. If we're going to find the y-intercepts, we're going to let x be equal to 0. If we let x be equal to 0, you know that you get y squared is equal to 81. And so y is equal to not just 9, plus or minus 9. So there's two intercepts, 0, 9, and 0, -9. And let me be more specific about that. There's two y-intercepts. So now let me let y be equal to 0. There we get 0 is equal to x plus 81. And so we get -81 is equal to x. And so the x-intercept is -81, 0. I do think they want you to list them out as ordered pairs. So you type all those in separated by commas, right, into the MyMathLab system, and it will immediately tell you whether you got it right or wrong. They also want to know about symmetry. So let's test symmetry. So let's first start with x-axis symmetry. My suggestion to test for x-axis symmetry would be this. Remember, it's x-axis symmetry, so you're going to let y be equal to negative y and see if x changes. So, or let me not even say if x changes. That's a little bit of a... Sorry, I didn't see that down there. And see if the equation changes. That would be... Let me say if the equation stays the same. If it stays the same, that's when you have x-axis symmetry. So here's the original equation. Y squared is equal to x plus 81. So what are we going to do to test for x-axis symmetry? We're going to sub out y for negative y. So let me do that in blue. I'm going to take what was y and place in a negative y. And then everything else is staying the same. So I'm going to put it in black. Now, what is negative y squared? Well, it's y squared. Does my equation look exactly the same as what I started with? And the answer is yes. And so the answer to x-axis symmetry is yes, x-axis symmetry. You absolutely have x-axis symmetry. So let's check for y-axis symmetry. So if we check for y-axis symmetry, we would, so for y-axis symmetry, we would focus on the x. We would replace, I'm going to choose different wording here each time, but similar. Replace x with negative x and see if the equation is the same. Okay, so original equation was y squared is equal to x plus 81. And so we're going to leave our y squared, we're going to leave our 81, but we're going to replace x with negative x. Well, that looks different. That is not the same equation at all. There's no way to get rid of that negative and have it look like x. And so the answer to this one is no. It does not have y-axis symmetry. Yeah, y-axis symmetry. I said that right. It's easy to get those words mixed up. And then remember with the origin what you do. With the origin, you replace x with negative x and y with negative y. And ask yourself, does the equation stay the same? Or is the equation the same? And so remember, we had y squared is equal to x plus 81. So what we're going to do, and I'll highlight it in blue, is negative y and a negative x. Come back to black. That was squared equals plus 81. Simplify it. So now we get y squared is equal to negative x plus 81. Those are not the same. There's nothing I can do to make those the same. And so the answer is no. It does not have origin symmetry. And you'll do that a few more times with just different types of functions. The best part is you're getting practice letting things be zero and solving. You get some practice with solving quadratic equations. You'll get some practice and get into this new idea of symmetry. So give that a shot and let me know what questions arise either by email or coming to the review sessions. All right, thanks so much.